We'll start recording. Okay, so we actually started off with looking at measures of the center. Just a quick review. We looked at last week. We looked at a lot of terms that we use, defining different the difference between a population and a sample. Remember, a population is every possible participant in a study that you could have. So it's like a census. We also call it a census. And a sample is a subgroup of that broader population. And then we have random sampling techniques, where several different kinds of random sampling, one of which is a simple random, which is every member of the population has a chance of being a part, has an equal chance of being a part of the sample. Okay, so if you were to do a survey, again, of say current salaries in Loveland, your sample would be all working adults, or your population would be all working adults. And then you would pick, using statistical guidelines for what would be a sample that would give you a good measure of that could be generalized to the population. These are generally done by using some guidelines that statisticians apply. So just say you decided that you needed to sample 1,500 adults. You'd have to find 1,500 adults that you could contact and get that information from. The method of choosing randomization has to be such that, if it's a simple random, has to be such that every adult wage earner in Loveland would have an equal probability of being chosen. How do you do that? Well, you can generate lists of addresses, phone numbers, a variety of different techniques can be used. But the key is that everyone should have the same chance of being included. Some of the examples we had in some of our homework looked at this. If you were doing a method of data collection that involved splitting the city into sections, and you were using that particular method of sampling, you would randomly choose the sections, but you would survey every potential participant in those sections. So you do a population of the section. So you do a census, and then you use that to generalize. Well, if you do true random sampling, then you have if you look at the city as a whole population, then the people in each section have a 100% probability of being included in the sampling. But then you can't have, it's not a simple random sample of the entire city, because any section that's not included, no one can be there. So we have lots of different ways of looking at how we structure these things and define it. And this is critical, because when you are reporting the results, you need to be able to justify the validity by using valid statistical methodology. And that is a valid statistical method. But it does mean that if you have a section of the city where either the mean salary is very low, or the mean salary, say, is very high, and those are not part of your sample, then you've lost some of the validity of the data. because you are excluding, some section that may have an effect on the results. Statisticians doing studies always are concerned that that their methodology is going to be attacked. And indeed, that does happen. There is, generally speaking, when we do these, we want to have as homogeneous a population as possible. Now, what does that mean? We don't think of our society as being homogeneous. We vary all over the place by ethnicity, by so-called race, by politics, by profession. There is no such thing as a truly homogeneous population. But what we try to do is wash out some of the external differences when we choose our population, so that we're not skewing the results. And can we pick a homogeneous population? Absolutely. Depends on how you want to define it. If we decided to survey all women in Loveland, that would be, by one definition, a homogeneous population, because every single one of them is female, right? If we are excluding any other factors. But if we were looking for Asian women in Loveland, that too could be considered a homogeneous population, except that no Asian believes that Asians are homogeneous. I mean, and indeed they're not. And what do you define as Asian? There's East Asian, South Asian, and West Asian. So you have to be very, very careful how you structure your population that you're surveying, that you're taking your data from. Sometimes it doesn't matter. I mean, if you're doing salary surveys and you've decided to look at all working adults, well, yes, there are differences. There are differences. There are some groups that can be shown statistically to have lower salaries than others. One clear example is that women generally have a lower salary than men. It has nothing to do with ability. It has to do with history and with culture. So we have to, when people are doing this kind of work, what we want to do is look at the purpose of the study. If the purpose of the study, for instance, we've seen this in many times. If the purpose of the study is to compare women's salary to men's salaries in comparable jobs, then we've defined a population. We may define our population as all chemical engineers, for example, working in some place where there's a lot of chemical engineering, such as big areas where petroleum processing is done. It's done by chemical engineers. So if you're looking at salaries and comparing salaries of women to men in a field, then you've limited your population, and then you've segmented the population. Okay, we've limited the population to chemical engineers in this particular study, maybe chemical engineers in South Texas, right? And then we've segmented it into female and male. That's perfectly legitimate as well. We can segment our populations because there are variations. The obvious one being the one we just described, men and women. But it could also be any other parameter you want. It could be based on years of experience. It could be based on age. It could be based on educational level. It can be based on a lot of things. And statisticians have to be very careful when they structure things and when you look at a report, You need to understand how they've gathered the data, what is the purpose of the statistical effort, how the data are gathered, and then how they're compiled. And again, you also want to know what are the criteria for including certain subjects. There are reasons. I mean, in the chemical engineering, you may want to exclude anybody above a certain management level because then salaries become, you can't really include management salaries along with the salaries of people doing the grunt work in the plant, right? So, again, you need to understand what your inclusion criteria have been. So each of those narrows the population. And then you have a choice of doing a census, taking all of the data. And remember, when we're talking about a characteristic of a population, we call it a parameter. If we, instead of doing a complete census, we take a sample, maybe we take 10% of our chemical engineers working in South Texas. That's a sample. Then the term statistic comes in. This is one of the definitional terms that we need to understand. A parameter is a characteristic of a population, and a statistic is a characteristic of a sample. Okay? So we have to keep these definitional issues very, very clear. That's why I gave you a definition sheet. I want you to refer to it on a regular basis because in any sort of science, and statistics is a science. It's a mathematical science, but it's a science. Is real dependent on definitions. We have to understand what people mean when they speak. So what we want to do is look at those kind of issues. And then there are, remember, we have qualitative and quantitative data. Qualitative data are things that aren't numbers. And there can be qualitative data that are numbers. The principal example your textbook uses is the numbers on the jerseys of sports teams. They're just identifiers. They have no particular order or meaning that we use. So, or zip codes. Zip codes are simply location identifiers, and that's it. So there's no rationale. In the same way that area codes for phones are basically location identifiers, because even in the early days there was no. I mean, you could generally say that the lower area codes were on the East Coast and the higher area codes were on the West Coast, and now they're all over the map. So there is really no particular order. You can't say that area code number 634 is in a specific location just from the number. You'd have to know where it is. Right. $719. Yeah. 720 now is the overlay in the Denver area. Yeah. 719 was Southwest Colorado Springs. Actually, anything basically south of Denver was 719. Yeah. Yeah. Right, and now telephone scammers, used to be that you'd get this number that would come in and it would be one of the known toll-free numbers. Now they've got the technology to make it look like it's a local number. And if it comes in and I don't know the number, if you're going to talk to me, you better leave a voicemail. If you don't leave a voicemail, then you didn't want to talk to me, or you're a solicitor. The other thing is my phone is now doing things like scam likely.
Yeah, right.
Yeah, and I look at that and say, thank you, click.
I don't know what I did.
Oh, yeah. Yeah, I'm getting really annoyed. I don't either. I don't either.
It was something but they did, you know, this is, this is Georgia.
It's an Android, yeah.
It started when and, of course, now.
Yeah.
But I think, what was the matter? Yeah, if I did it, for this part, I have to deal with it. Do something before I can do it.
Yeah. Yeah. So anyway, that's that's a little off topic, but it is something that is bothersome to many of us. But if we look at our data, then we have the difference between discrete and continuous data. We had quite a discussion on this on Monday because it's really, to some extent, it's a subtle. I mean, we look at data and we say, well, that's a discrete number. Well, sort of, but in reality, if we think of discrete first as integers, can the value only be integers? Okay. One example was number of babies of College America students. I mean, you can't have half a baby. Really? You can't. So you can't. So, those are discrete numbers. 1, 2, 3, 0, 1, 2, 3, 4, etc., up to however many, up to however many we have. And so, however, scores on exams can be a wide variety, including fractional scores, because some of us give fractional points. And if you look at some of the exams that we have, even in Canvas, if you've got a multiple select or a matching, you can have scores that are not integer numbers. Yeah, so those then are, at least if you look at it that way, they're continuous data. And the other side of the baby question was the weights at birth. Well, Richard pointed out that the number that you have at birth is a discrete number. But the problem is that babies don't come in nice even numbers of pounds, or so it's a continuous data set. They can be any value. So you need to think, when you look at the difference between discrete and continuous data, what you have to look at is it possible for there to be no gap in the continuous stream of potential answers? And yeah, right. So it's a continuous data set. So again, it's a case of looking at what the data definitions are, and then looking at some of the more subtle definitions like nominal, ordinal, etc. If you need to be looking at, and again, it's critical. I mean, it may seem kind of silly if you're not doing a lot of statistics. Thank you, and you. It may seem kind of silly, but in reality, The kind of data that you're looking at predicts what the data will look like. Nominal data, such as colors or favorite movies or anything, there's no order to them. I mean, we can impose an order. We've got the rainbow, Roy G. Biv. We can arrange that, and we can look at a progression. But in reality, that's just an artifact of how we look at it. There's no real order, and there's no regular difference. In fact, you talk about a continuous data set would be frequencies of light, because it doesn't just give you red and orange and yellow. There are all of the minuscule shades in between. Just go into the paint section at Home Depot and look at the color cards. I mean, whatever, there is it's a continuous data set, colors, in that respect. But if you're looking at people's favorite colors, there's no order to that. People who like red are not better than people who like violet, or bigger or smaller or anything else. There's no correlation there. Then you have others that you can look at regular differences, but there's no starting point. There's no 0 point. An example in your book is years. There's no year 0. I mean, we artificially place a year 0 around the birth of Christ in this society, but that isn't year 0 for the Jews or the Hindus. So again, there's no natural 0 unless you go back 4.5 billion years. And we're not interested in that. Nobody cares that this is year 4,675,000,000, etc. So there are, and then there is our ratio data, which is exactly, there is a 0 point. If you're looking at scores of exams, you can't have a 0. Somebody can literally get everything wrong and score 0, And there's also a natural top, but there's no problem with having a natural maximum. 100% is a maximum, but that's only, again, a calculation. A test can have 5 questions or 55 questions, doesn't matter. Okay. So you do have a natural end, but that's not the issue. You have a natural 0 as well. And each score in between, doesn't matter if we have a discrete data set or a continuous data set, you have an orderly progression of scores. 1 is better than 0. Maybe not much, but it's still better than 0. And of course, 95 is better than 90. We all know that. So we can put all these things in order. So again, we're looking at understanding the nature of data. And that's important depending on the application. The applications in business, such as your hotel management, you have literally discrete data points. You have so many beds to a room. You have so many rooms in the hotel. Some of those rooms will have one large bed. Some of them will have some number of smaller beds. You also have then a theoretical maximum number of people who can actually stay for a night. You have a maximum number of rooms that can be rented for a night. And you do all your statistics based on what proportion of those rooms are regularly rented out. And, setting aside corporate policies for keeping a few rooms for emergencies and that sort of thing, which I know hotels have. What you're aimed for is some average level of occupancy to make the business profitable. And your pricing reflects that as well.
And it's the most expensive because we only have one. And they're both pretty good. You have two beds, one king size bed, and the jacuzzi. That way you can get up and slide in if you want. But we recently had an issue in that room where somebody put the red button long was what was supposed to start the jacuzzi.
And it was emergency button.
Yeah, it's supposed to stop. And they had to turn it on. They couldn't figure out how to turn it on. So they hit the button and they pushed it over there and left.
Oh,
And I said, "You can't hit the button on the wall." And the person that took it over, they couldn't get the button up. I said, "What button? Don't turn it on like that." I said, "I know." They told them to slowly put the button back out and flip the switch. And they wouldn't pull it up, and the whole button itself came right off the switch,
yeah,
and they still couldn't get the jacuzzi set.
yeah.
And they were so mad. She's like, "We told you to push the button. It's a red button."
And you have instructions for how to turn it on in the room. Yeah, yeah,
Yeah, the little settings. And then the switch. And the switch is over here, and the button is over here.
yeah.
And yet, everybody wants to hit the button. It's the red button. So I'm listening to it.
Yeah. Does the idea that a stop sign is red ever occur to you? I mean, yeah. But yeah, again, you have those kinds of statistics. So you have in that respect, your much of your data is going to be discrete data because you're not going to put 1.5 people in a bed, right? Yeah. Yeah, those rollaways aren't comfortable. So yeah, sofa bed. Yeah. Yeah.
I can't believe your mattress is like this. It's great. And it was still in plastic. And I said, good news is that the kids won't be sleeping on anybody else's joints. They should just, yeah, but the mattress is so thin, I can see what I'm doing. So we grabbed one of the new rollaways and we tried to put that mattress on top. It's smaller.
Oh.
No,
Yeah, right. Yeah.
So, so that it would be somewhat better. The sun got out. Ooh, there's an animal. I think that's a because neither kid wanted to sleep. My mattress feel the springs in it and ran along so upset. She was very distracted. I need one and you go to the house. They're like, it's a cut, yeah.
Yeah, it's
hold it in somehow.
it is yes, they have not improved that technology. Okay, so remember we also talked about frequency distribution which is useful on data sets that are not really small. You have less than 10 data points, frequency distribution may not make any sense, simply because there isn't enough data. The data set we looked at the first week involved pulse rates in women and men, and there were like 40 data points. There, a frequency distribution can make some sense. But again, when you get up to very much larger data sets, and what's the maximum depends on your data, depends on what you're trying to do. But when you get up to a large enough data set, and frequency distribution is not necessarily a good way to look at the data. There's when we start looking at histograms rather than a frequency distribution table. So there's lots of ways of presenting data. And pie charts, we talked about pie charts. There are advantages and disadvantages to all of these methods. But the issue is that in all cases, they're only meaningful if we set them up so that they can be read easily. We have to include all the data. When you start excluding data, you start misleading people. When you look at any of these things, what you want to do is what are they saying here? And look at how the data are being displayed. Remember, our biggest one was, when you have a y-axis, a vertical axis that doesn't start at 0, then your data can look very different than if it started at 0. So again, when you are looking at data, one of my suggestions is look at the data, and if people are presenting, especially data they're presenting without a 0 point on an axis, redraw it with a 0 point and take a look at it and see what it tells you. Because statistics, unfortunately, are abused by an awful lot of people. Advertisers are the biggest sinners in that one. But politicians use statistics as a propaganda tool a lot. Politicians from every point on the political spectrum do the same thing. They have a message that they're trying to deliver. So that's the other thing to look at when you're looking at statistics in general, is what's the purpose? What are they trying to convey? So we'll go back and we'll take a break right now, 10 minutes, and we'll come back and talk about, I'll just do a quick review of measures of center. And then we're going to go on to looking at variation from center. And we'll talk about the concept of a standard deviation and what that means. Okay? All right, let's take a break. Okay. So let's talk about next first. Next week, we are going to be covering chapter 4, which is probability and probabilities. This class, probability is an important area of the statistics in that it is looking at the likelihood of events occurring. The simplest example is rolling a die, single die. You roll it, you've got a 1 in 6 chance of coming up with any number you choose. Okay, if you choose it, if you want to roll a 3, you roll the die. Your chances are 1 out of 6 that you're going to get a 3. If the die are on, if the die is on. so we have to assume that it's honest. So the what I want you to do is read chapter 4. Look through the examples because we have no class on Monday. We're closed on Monday. So it's President's Day. So we are not here. But that doesn't mean that we're not going to cover the material. So what's going to happen is you're going to read the chapter on Monday and start looking at the homework assignments and start looking at what we need to do. And then on Wednesday, we're going to do what is called an inverted class. In other words, what we're going to do is come in and work through examples, and you guys are going to work on the homework on Wednesday of next week. And we'll work on that in class. We'll work through a number of examples from the book of the various kinds of calculations that we do, and then we'll do the class in that way. You're going to have to do the reading and studying outside class to be prepared for the class on Wednesday. So please don't put that off. And if you're going to have a hard time doing it Monday or Tuesday, see if you can do it over the weekend. But we want to be prepared. So that's how we're going to run the class next Wednesday and for the week. Okay. So let's do a quick review of measures of center. Okay. And then we'll talk about. Then we'll move on to looking at variations. Yeah. That will actually be coming up real soon. Yeah, it should be in the book. That table ought to be in the book. It also is as an appendix. It's Appendix A3, I think, or something like that. So it's a pullout in the text, which obviously yours got pulled out. It probably disconnected because it's just perforated in. But it also appears if you don't have that particular table inside chapter 3, it is it's an appendix to the text as well. Also, the data are available in the text CD that's in the course home. Those tables and everything out of the back are in there. The text CD is actually online as well, April, in the Canvas shell. So what are we looking at in terms of measures of center? Okay. One is what we call the mean. The mean is what most people call the average. The easiest way to calculate a mean is to add up all the data values and divide by the number of values. So if we've got, if we look back at that first week at our 40 pulse rate numbers, if we added up all of those numbers and divided by 40, we'd come up with an average pulse rate for women for one set of data and men for the other. What that tells us, I don't know. Because again, the only purpose for doing this is to have a reason for wanting to know what that average is or what that mean is. Again, statisticians prefer the term mean as to average because average is used in too many different fields. We talk about the average lifestyle. We talk about an average person. These are kind of meaningless concepts. Whereas the mean has a very specific definition, which is exactly that. You sum up all the data points and divide by the number of data points. This works well with data that are distributed evenly. across a data set. But if you have data that are not distributed, if you have data where you have a set of numbers and then you have an extreme. One example in the text has been salaries of college football coaches. Okay, if you look at the bulk of the data, then it's in a relatively narrow range of salaries. But there is the occasional one that gets paid a really high salary. You know, you'd expect this to be like a big salary. That what you get an inaccurate level or an inaccurate and what it says is what they're going to have is then, if they just look at the mean or average salary, they're going to have a different expectation than if they were looking at maybe the salaries of tier 3 schools, because they're going to be lower, right? Oh yeah. Yeah, we'll take a break in about a half an hour. So so what happens then is we want to take what is called the median, April, and a median is essentially it's the exact center of your data set. So what you do is you line out all the numbers in order and pick the one in the middle. If it's an odd number of data points, then the one in the middle is going to fall directly on a value. If it's like 17 data points, then we're going to have number 9 is exactly midway because there's 8 on one side and 8 on the other. Okay. If it's an even number of data points, then we take, like if it were 18 data points, we'd look at number 9 and 10 and take the mean or average of those two, and that's our median. You'd add them together and then divide by 2. Okay. When we are talking about taking a mean, what we're saying is we add up the data points and divide by the number of data points. In this case, we're looking at 2 data points. So we're adding them up and dividing by 2. Okay. So that is a much better idea because it is what we call resistant to the effect of extremes. Now, you can have extremes on either end, low extremes and high extremes. Okay, and data sets can be skewed in either direction. If they are equally skewed in both directions, we consider it a normal distribution, and we don't have to worry about the difference between the mean and the median. Another method of looking at the midpoint of data is to look at something we call the mid-range. The mid-range is simply looking at the highest data point and the lowest data point, adding them together and dividing by 2. Again, this is not a resistant form. It can be very much influenced by outliers, by extreme data points. So it is something that we use, again, limitedly, or we use it to look at either small or relatively compact data sets where we don't have a lot of extremes. The difference can be seen in looking at some kinds of data. There was a problem that we looked at where we looked at satellites, space satellites, put up or sent up by 17 different countries. One country had 156 satellites. The next highest number of the other 16 was 18. And the most common number was 1. So if you wanted to know what the average number of satellites put up by countries that put up satellites, again, we're defining our population as countries that have satellites in orbit, by either launching them themselves, and we just had another country join the family of countries that has the missile capability to put a satellite in orbit, and that's India. Just did that. Or under contract to either the European group, Arianespace, or NASA, or SpaceX, Elon Musk's company, or Blue Horizons, Jeff Bezos' company, the commercial launchers. But if we looked at that and we averaged that set, took a mean of that set, it's going to be, the mean is going to be way high because of one country, obviously the United States, with this 156 satellites. So there's another method, which is to delete from our calculations the highest 10% and lowest 10% of the data set. So in the case of this data set of 17 countries, we'd eliminate the 156 and the 18 as the two highest data points, and then eliminate 2 of the ones. And then we have a much more representative data set. There are arguments for and against all of these methods. Another method, another term we use is the mode, April. The mode is the value that most often appears in our data set. And we can have, and so you have a data set and it might have, 20 different data points. And you might have 4 of them might be, say, 6. If there's nothing else that has 4 or more data points, then 6 is the mode. The theory here is that this is more representative of a real mean. The country, the list of satellite countries, the mode was 1 because it appeared about 8 times. It's much more representative of what random company or country that puts up satellites would have, because it's the most common number. Now you can have several appearances of data points with the same number of appearances. Let's just say it out of our 20 data points, we've got 4 that are 6, and we have 4 that are 12. You can have multimodal data sets. You can have more than one mode. If there are 2 of them, we call it bimodal. If there are more than 2, we call it multimodal. It's sort of like the old, the old counting system that is used in some of the primitive societies, some older societies, where they have 3 numbers: 1, 2, many. Okay. So, but the issue is that that we can have. This is also a measure of not necessarily the middle of the data set, but as the most common occurrence, it is more representative of what is a likely value in the data set. Okay, so it's not truly a center, but depending on the kinds of data, it may be more representative of concept. We talked about the mid-range, which is the highest value plus the lowest value divided by 2. Again, it is a good way to estimate where the middle of the range is. And it's if the data points are fairly smoothly distributed, and I'll draw that out on the board in a moment. If they're fairly smoothly distributed at that point, then the mid-range is a reasonable way to estimate where the center of the data lie. Why do we care about that? Well, we'll come to that later when we start talking about deviations from center. We can use the frequency distribution. I was talking to Brandy about that when you came in and when Richard came in. When we look at, we can use a frequency distribution plot to calculate. Now, there's a couple of things that we can do. The problem with the frequency distribution plot is that we've grouped the data into classes. In the case of and the number of classes we choose depends on the distribution of the data, okay? The range of the data. Now, the range of the data is, again, now the difference between the minimum and maximum. That's the range. So in our data set that I mentioned before of 20 data points, if the range, if the lowest value was 2 and the highest value was 18, the range would be 18 minus 2, or 16. And if we were to put classes on that and divide and decide and try to define what the width of each class would be, we want to know that range, and we decide on the number of classes we want. In this case, I'm just going to randomly pick 4, largely because 4 divides into 16 an even number of times. So we would have, if we did 4, then our class width, when we're doing a frequency distribution, class widths have to be identical. So in this case, the class width would be 4, and it would start at 2. Now let's just decide to say we decided we wanted to have a class width or a 3 ranges of our data. And again, we've got 16 divided by 3, that's 5, right? That's 5 and a third. We always round up. So now our class width, if we wanted 3 ranges, our class width would be 6. And we would start it at a way that would give us data in each class. We could start it at 2 still. So it'd be 2. The next class would start at 8. The next class would start at 14. Or we could start it at 1, and then 7, and then 13. Depends on what we're doing with the data. But the issue is we're trying to establish then how often things appear in those ranges. Note that it doesn't matter what the value is in the range. If we have that range from, say we've decided on 4 classes, and we have ranges then from starting at 2, so we have 2 to 6, and then 7, or 2, 3, 4, 5, 2 to 5, 6 to 10, etc. Goes through 11 to 14, and then 15 to 19. So what we have is if we have 2 data points that fall into that first range, 2 to 6 or 2 to 5, we don't care what their actual values are. All we care is that they fall into that range, right? So yes, we know what the data, especially if we have a small data set, we know what all the data are. But if just assuming we have a large enough data set that we don't care, or if we're given a table, which you will be in the homework, given a table that just lists the frequencies, if we want to use the frequency plot as a means of estimating the middle of the data set. Now note that I've been using the term estimating. all of these things are really estimates of the center of the data set, with one possible exception, and that's the median. Okay? But all of these are an estimate, and they serve different purposes. But if we use the frequency plot, and we have a frequency range of 2 to 5, then the middle of that range, 2, 3, 4, 5, the middle of that range is 2, 3. Okay, so the middle of the range is 3.5, right? Because we've got, or 3.5, because we have two points on one side and 2 on the other. The middle of that, and there are 2 values in that frequency. We multiply the middle of the frequency range times the number of values in there. So now we've got 2.5 times 2, so 5. We do that for each range, for each class, total it up, and then divide by the total number of data points. Does that make sense? As I say, that's an estimate, because we really don't know in that first range, 2 to 5, if all the numbers are 4 or all the numbers are 2. So we use this as an estimate. Large data sets, well, generally, if we have large data sets, things are going to be distributed throughout the classes. And so it may not, you may get closer to a true mean. But again, we're looking at the mean. But if we look at the blood pressure data or the pulse rate data for women, note that the bulk of the data were in the first 3 classes. And then we had 1 data point in the next class, 1 data point in the next class, none in the third class down, and then 1 in another class. So the data were skewed. So using the frequency distribution is not necessarily a resistant measure, especially if we have extremes in the data, low or high. So again, when we're looking at the center of a data point, what is our purpose? If we're doing a salary survey of working adults in Loveland, it may make sense in terms of, let's just say the city is trying to determine, the city is trying to determine what kind of total income is available and how that translates into revenue for the city, right? Because the state does share some of the tax revenue that we get with the cities, and it's dependent on the amount of money that is made. Okay, so your average salary, irrespective of position or profession or anything, makes more sense. The mean of that data set makes more sense than worrying about extremes. So again, your measure of center is going to depend on what you want to do with it. Okay, does that make sense? All right. Then we have something called a weighted mean. Sometimes data can be, depending on what you are looking at. An example in the textbook was a question of how you would calculate, say, an average income in the United States. Well, one way to do that is to take IRS data and just total up the entire reported gross income that appears on your tax statements, and then divide by the number of tax statements. That would be one way of doing it. But the example in your book was to look at states. If you just took and went by state and determined an average income per state. Okay, so then added up the average of each of the 50 states and divided by 50, you're not going to get an accurate number, because some states, like California, have like 40 million people, 40, 50 million people living in them. And other states, like Wyoming, have 1% of that population. And so the data are heavily weighted, here toward, or heavily influenced by what goes on in California. Also in California, we'd expect the mean salary to be higher than in Wyoming. Not to say that there aren't some people in Wyoming that make very large salaries. There are. But most of them, if you drive through Wyoming, if you know much about Wyoming, you know that many of the people are farmers, ranchers, or Native Americans with subsistence income levels. So we'd expect the average income there to be low. So that's where a weighted average comes in. And the weighted average would then include a factor for the population of each state. That factor could be based on the absolute number of population, or it could be based on a ratio, a percentage of the population of the country that lives there. And again, when you look at data like that, you have to ask yourself, are we only looking at wage earner data? Or are we looking at total wages, and irrespective of whether everybody's working or not? And of course, these days, there are a tremendous number of people, especially in my age group, who aren't necessarily making money, but working very hard. They're taking care of parents. They're doing a lot of things. So there's a lot of other factors to consider that when you look at that. But the fact is that if you wanted to look at a true average salary, you would have to weight the data. You couldn't do it by just averaging up what each state had and then totaling that. So you'd have to weight it somehow. So we use that. So I'm going to go up to the board for a minute, and not charging very quickly. All right. Trying to charge my phone through the computer. I'm sorry? We are going to look at variation today. Okay, we're going to go through that. But I would like to look at at how we look at data. Okay. And I'm going to do some drawing on the board to that extent. Let's take a look at a histogram of the data on pulse rate in women. And we look at a histogram of that data. Remember, there were ranges here of 60 beats per minute to 69.9, etc. I'm going to round everything off to make it a little bit easier for me to draw it out. A range of 60 to 69.5. So we've got 70, 80, 90, 100, 110, and 120. And then we'll put them on 30 there. Remember, there were, in this first range, there were 12. The second range, 14. The third range, 10. Fourth range, 1. This range 1, none in the next range, and 1 here. So these data are what we call skewed, meaning that if we drew this out and put a curve that went from the top of the middle of each one of these, it would look like that and would actually drop to 0 in the middle. So the data have outliers. So this is a skewed data set. If we were to do a smooth curve of this, it would start at 0 because we have no data points below 60, right? It would start at 0 and it would look like that with a big tail on one end. This is a skewed distribution. Skews can go in both directions. A normal, what we call a normal distribution, is what a lot of people call the bell curve. In other words, it looks pretty much 1/2, if we drew a line down the middle, 1/2 is going to look like a mirror image of the other. One side will look pretty much like a mirror image of the other side. Okay, that make sense?
Yep.
Okay. Quite frankly, small data sets are often skewed. If we look at, for instance, if I look at exam grades for a class of maybe 10 students, we're not going to have a smooth distribution. You might have one student who gets 100% on an exam. You might have another student who gets 50%. But most of them are going to fall into a range around 70 to 80% on most exams. That's the way most exams are structured, to where you'll see some differentiation. And then you'll have some people that'll have lower scores and other people that'll have higher scores. Small data sets tend to be a little bit skewed. Large data sets, however, start approaching what we call the normal distribution, the bell curve, where we have the vast majority in the middle, and then smaller numbers going out on each extreme. Data sets can be analyzed, even skewed data sets can be analyzed in this way. Let's just take a look at, I'm going to draw another curve here. We'll look at the concept of variation in data and how we calculate that. And remind me, please, before you leave, to make sure that I make a change in the 120-point assignment for this week, because there's part of that that really is not going to be covered until the 4th week. Okay. So, or no, that's not the one I gave you. It's one that gives you a series of problems. Yeah, questions out of the book, and I want to modify that because there's some things there that just are not going to be covered. Okay, so if we look, and I'm going to use a normal distribution here, roughly. We look, there's always a center point. Okay. Okay, I'm going to call that 0 for the center point. And then there's a side that by convention is the plus side above 0, and a side that's the minus side or below 0. There is a measure of center. There is a measure of variation in data that is called a standard deviation. And I want to get to that here in um, in a second here. Standard deviation is basically it's a measure of variation of values around the mean. What's the purpose of standard deviation? In large data sets, there are going to be variations. And what we are looking for is the standard deviation really is a definition of what we would normally if we were looking for the issue of standard deviation is kind of wanted to say right now, we have just going to give you some rough issues. Standard deviations are such that if you have a large data set, we've got -1 and +1 standard deviation. Roughly between these two, 68% of the data will fall. In other words, about 2/3 of the data, a little over 2/3 of the data, will fall within one standard deviation of the norm, either plus or minus, so 34% on a side. 2 standard deviations takes this out even further. 2 standard deviations, 99% of the data. So what we use for this is to determine whether something is outside normal expected values. In other words, we expect 99% of the data to fall within 2 standard deviations of the norm. Now notice I haven't really put a number on the standard deviation because the standard deviation is going to be different for every data set. The standard deviation of a set of numbers of, say, from 50 to 100 is going to be different numerically than the standard deviation for a random set of numbers from 50,000 to 100,000. So even with the same number of data points. So we want to keep in mind this is a concept, sort of an empirical rule, we call it. Rather 95% of the data within 2 standard deviations. Now, we will never get to necessarily get to 100% for the simple reason that if data can fall outside multiple standard deviations. But anything that is considered that is more than 2 standard deviations, either positively or negatively, from the middle of the data set, which is defined as the peak of this curve, any of these things are any of the standard deviations, anything that falls outside 2 standard deviations is considered outside the norm. In other words, it's outside the expected set of data. And so many times when we look at things like, say, the repairs of automobiles. And again, we can't compare across brands, but within a brand, we can expect we can actually predict for a specific kind of repair what it should cost. And if the cost goes outside the norm, then we have a problem. Okay. We can also look across data, although that's risky to start looking across because different cars from different manufacturers have different costs. Well, and yeah, and it depends. You know, the cost of repairing a Rolls Royce is a heck of a lot more than the cost of repairing a Ford. Rolls Royce, that is a British luxury car, a standard. Bugatti actually is probably even, yeah, they're probably, but yeah, yeah, Bugatti's different, yeah, that too, but yeah, yep, yeah, very specific design, very expensive automobile, and very costly to maintain. So, so we have that. So again, empirically, 68% of the data should fall within one standard deviation of the norm, which is basically the mean of the data set. In this case, we look at the data set and just and average it out. 95 within 2, and 99.7% of the data will fall within 3 standard deviations of the norm. Standard deviation is a number. It's an amount of it's a distance from the center of the data, and so it's an absolute number in each data set. But the standard deviation is basically is a measure of how the set varies. And again, depends. I showed a rather sharp curve. If the data set, if the curve for this data set looks a little differently, such as maybe wider than that, then the standard deviation is still going to be the same ratio. 68% of the data will fall between plus and minus 1. But that width of that standard deviation is different because the database is wide. Okay? Again, the standard deviation as a concept is dependent on the variance in the data itself. Okay, the variation in the data itself. Let's stop there for now. We'll take a second break. Come back in about 10 minutes. We will keep going. Okay, we've resumed recording. All right. Obviously, if we have a very smooth set of data, then the mean is going to be right in the middle, as is the median, pretty much, right? Theoretically, your mode should be there too. If you have a large data set, your mode ought to be right about there. Okay, so our measures, and if we have a very smooth, then our mid-range, which remember is not the best estimate because again, it's much more susceptible to extremes. But our mid-range in a truly smooth data set, which is what we call a standard distribution, is going to be approximately the same thing. So in a data set like this, our standard, our measures of the center are all going to give us essentially the same answer. But if we look at a data set that is, say, skewed out to there, then our mode may be there. Again, we'd expect the peak of something like that to be the place where we see the most data points. So that might be the mode. X bar, however, adding all up and dividing, might be over here. Clearly not centered. Mid-range is going to be halfway between these two. So our mid-range may be here. Okay. And our median is going to be somewhere past the peak. So our skewed data sets are a little different thing to deal with. However, what we're doing when we calculate a standard deviation is we're looking at all of the data points. So we're looking for standard deviation is a measure of variation from the mean, wherever it has to lie. So we calculate X bar. Calculate X bar by the standard method. Add them up, divide by the number of data points. That gives us X bar. So when we are calculating a standard deviation, there's a couple of formulas. We're going to concentrate on just one because the other is something that's used by calculators and spreadsheets and stuff. But it is the standard deviation for a sample. Standard deviation for a sample. I'm going to call that SD sample. Is abbreviated S. And it is, in reality, the sum of X minus X bar squared divided by N minus 1, divided by 1 less than the total data set. There are lots of mathematical reasons for that, but we'll just accept that. So what we do is we look at each data point. No problem, Kevin. Or Kevin, excuse me. So we look at this for each data point and calculate this. And so we calculate the difference between the data point and the mean of the data set, and then square it. Obviously, we always have a positive number. Okay. So an example that's given in your, yes.
So,
Yeah. It can be a decimal. Well, we always round decimals. I mean, because decimals don't necessarily come out to be nice rational numbers even. But round them off to the extent that you need to. But always, generally speaking, you want to round off at most to 2 decimal points. I say at most because after that they become the differences become ridiculously small. 1,000. So we just don't bother. And use the standard rounding rules. So pick your rounding point and then look at the next decimal place. And if it's 5 or more, increase the previous by 1. If it's less than 5, simply drop the rest of it. So depending on the data set, you're going to have lots of decimal points. Okay? So don't worry about it. Now, that's for a sample. Yes. Oh, sorry. Yes. S equals. S. So S is the standard deviation for a sample. The same equation applies to a population, but the standard deviation for a population is the Greek letter sigma, and that equals the same thing. So when we see a standard deviation listed as S, it's from a sample. We see it listed as the Greek letter sigma, it is from a population. Note that the population numbers are either, and remember that in a population, okay, now it's going to actually be, the formula will look slightly different in that we have the sum of x minus x tilde squared. Remember, that's the mean of a population over capital N minus 1. Capital N is the number of samples, or the number of data points in your population. Okay, so remember that we have, but the formulas are calculated exactly the same way. We look at the difference between the specific value that we're looking at and the mean. So let's use again the example they use in the book, which is a very small data set, 3 numbers, 1, 2, and 14. And the issue is, obviously, this is a skewed sample. So 1, 3, and 14. Let's use 3. Use the book. This obviously is a skewed sample. We've got 2 small numbers and then a big one. Now, we don't know what this comes from, so it's irrelevant. But we can use this to calculate what we want. We can add this up. We have so we want to calculate X bar. We're going to call this, we're going to assume this is a sample. So this is going to be, remember, the sum of X over X, the sum of X over X, right? So that becomes 1 plus 3 plus 14 over 3, which is 6. 1 plus 3 is 4, 14 plus 14 is 18, divided by 3 is 6. So the average is 6, the mean is 6. So now we add up, we want to calculate a standard deviation. So the standard deviation is going to be, again, remember, it's the sum of the differences. So we've got 6, or 1 minus 6 squared plus 3 minus 6 squared plus 14 minus 6 squared divided by 2 in this case. X minus 1, N minus 1, right? There's 3 data points, so we divide by 1 less than the total number of data points. So 1 minus 6 is 5. 5 is minus 5. 5 squared is 25. 3 minus 6 is minus 3 squared is plus 9. 14 minus 6 is
7 is 8, rather. Squared is 64, all divided by 2. We add that up, that's going to be 34 plus 64 is 98. 98 divided by 2 equals 49. Right. Good. So that's 49. So the standard deviation is the square root of that. Remember, the standard deviation actually needs to have, there's another part of this formula I keep forgetting to put in. It's the square root of, remember the square root of these numbers. Sorry about that. That's on your definition sheet there.
So then you would use 7 and go to the mean and subtract the mean from 7? Or I'm sorry, we go out 7 from the mean in each direction?
Mm-hmm. So our mean is 6. So our standard deviation is 7. You can see that when you have a skewed data set, your standard deviation becomes, it's large. Okay. Large, in this case, larger than the mean. But we can calculate that. Okay. We can calculate that for any data set we want. Let's go back. Remember at the beginning of this chapter, the question was, do men or do women talk more than men? And remember that was this question at the very beginning. And we had some information, a sample size and a sample mean for men and women. So if we look at that and look at the data, and compare different samples, what we have is understanding here that if we're comparing groups, the means have to be fairly close. In this case, the means for men and women are pretty close. The standard deviation, if we go through the calculation, we don't have the entire data set. It is in the I think it might be actually in the data set 8 on page on page 775. We have the full data set of all of the samples. Okay. If we do this calculation, what have we got? We know the median, we know the mean, and we can, if we go through the calculation, we calculate a standard deviation of 8.63, 8,632 and a half for men and 7,301.2 for the women. If we look at our data set, we can see that the data set is really spread out. It looks like the minimum on the men is about 1,118. The minimum on in the women data, again, you have to line this out, obviously. Is a bit higher. 5112 is the smallest value I see. So what we have is standard deviations here and comparison of those populations when we're looking at these things. So now we want to look a little bit further at how different these populations might be by analyzing. You know, we have a lot of numbers, and trying to have this lined up. So the standard deviation for men was higher than the standard deviation for women, which means the data set for women is more compact. There's less variation. And so what we want to be careful is not to read too much into such data. Standard deviations depend on the data set. We have a standard deviation of 7 in this little bitty 1-3-14 data set. Standard deviation in the data set for spoken words by men is very much higher, but then the mean is also very much higher. And again, if we look at the standard deviation, and if we look at, if we plotted out these data, of course, we're not going to do that right now. We plotted out these data, then what we would have is probably pretty much a standard distribution. And so it's hard to draw a lot of conclusions, but if we look at this, the mean for women is slightly higher, the standard deviation is slightly lower. If we look at the median, again, we're looking at a data set. The median is not all that different for the women from the mean, but for the men, it definitely there's a greater difference. So the data sets are not really, are not necessarily real smooth. Again, okay. So what we're doing is we use these as various measures for the if you will, the quality of the data we've accumulated. And the larger the data set, the better. Your book is full of large data sets, but we don't do a lot of those problems. So let's take a look at how another way of using this. When we have two different sets of data, we need to look at something called variance. And variance is a term that has a very specific has a very specific set of definitions. Variance is calculated slightly differently. The variance for is really the square of the standard deviation. And the square of the standard deviation is really closer to for a sample is closer to that of the population itself. The units are different as well. The variance here gives us a very simple way, well, not simple, a way of looking at how to compare data across data sets. Okay, well, here we're talking about men and women, but we're really trying to compare two different data sets, and what we want to do is look at how the variation relates to the standard, to the data set itself. So we're gonna keep going on talking about standard deviations for a little while before we get into what we do after we have those. We look at something we call the coefficient of variation. Okay, and we use it for we can use it for sample or population data. Coefficient of variation is simply the ratio of the standard deviation to the mean, to X bar for a sample, or to mu for a population, and then just call that and then multiply it by 100 to convert it to a percentage. So the data set that we're working with men and women and their words, when you're working with data sets and comparing data sets that have similar means, the coefficient of variation allows us to compare this quite a bit more easily. So the standard deviation for for men is 8632.5. Write that down. So the coefficient of variance is S over X bar for times 100% for a sample. So we're going to use that. In this case, X or S is 8632.5 divided by X bar, the mean, 15668.5. Someone have a calculator and do that right quick. Divide 8632.5 by 15668.5. Well, it should be 0.5. We're dividing 8632.5 divided by 15668. So what is the number? 5 what?
It's 0.550994.
Okay, so we're gonna call that 55.1%. Round it off. 5509, right? Round it off. Call it 55.1%. That's the coefficient of variance. Let's take a look. This is for the men.
When I did, I'm sorry, when I did that thing, like,
Then I check your numbers.
I did 3 times.
Okay, we'll have to look at that. All right, let's take a look at the number for women. For women, it was 7301.2. That's the standard deviation divided by the mean, which was 16215.0. So, and then times 100%. And what's that number?
.45.
So this is 45%.
Which
So,
logically makes sense.
pardon?
Which logically makes sense.
Yeah, 40, so the measure here, the measure here tells us that there is a significant difference in the compact nature of the data. In other words, men have much more variation in the number of words they use in a day than women do. I don't think you can come up with any much more than that. Okay? But we do have these various means of analyzing, of looking at the data. So let's keep going. Go ahead.
Okay.
So again, we have different kinds of, we have two different populations here. One is the population of women and one is the population of men that we've taken our samples from. When we're looking at differences in the data, the quality of the data, the coefficient of variation is a measure is a different measure of what we're seeing. So even though these things, even though it does look as though men and women speak with essentially very close to the same number, if we look at the means, what it tells us is that these data, the variation here tells us that the data themselves are significant, that there is a difference. The magnitude of that difference is irrelevant. What we've done is determine that our data sets are valid, and a conclusion that women probably use more words in a day than men on average. Again, you can't say that this applies to any individual. Is really a valid statement.
If they're doing a study like that, they have to exclude certain professions, I mean, the teacher, I'm assuming they probably cover that. you know, or B at the higher or something.
Yeah, all we,
That's what it
yeah.
is.
Some way or another, naturally more verbal occupations would have to be either excluded or made a separate study. But that's a good point. And we don't know how they selected. Okay. Or how they did the study. So, questions? All
Can I ask a question about the homework?
right, we can.
I've typed it 3 times and I can't get it. Yeah.
Which
I'm
number?
getting like 2 something, but these are all 4.
Okay. So you are looking for the coefficient of variation.
Right.
Okay, and then compare the variation. Okay, remember the coefficient of variation is determined by, no, these are numbers, okay?
Those are the
What,
values.
those are the values. So you determine the mean, and then you determine the standard deviation.
Which I did. Which is right here, which is 27.5. Because it comes out to 130.
All right, now, the range here goes from 118 to 131. That's the range. Right, those are the, to the min 820 to 21. The range is 118 to 131, which is, did you take the square root of that?
That's all.
Okay, so here the range is 100 to 131, right? That is 13. Your variance there, your coefficient of variance is twice as big. So
the range, not
you don't, you use the mean, you calculate the mean, so you calculated the mean of 124. So, yeah, so we have 4.3 squared plus 0.3 squared plus 5.7 squared plus 6.3 squared plus 6.7 squared plus 1.3 squared. We take the square root of that. The square root of 137.34 is not 27.
Type the square root.
That's the square root.
It's not divided by.
No. Well, we divide, first off, you divide by n minus 1. Which is gonna be
Well, no, I already squared them. These are all the squared numbers. Add it up together. Then you square it again.
no. You take, you square them, add them up,
Alright, so, right.
divide by 5. Remember, you're dividing by n minus
0.43. You get 0.43, right?
1. Yep.
So
No,
then I go
you get 4.3.
times another negative 4.3.
Yeah.
Equals 18.49.
Yep.
Which is exactly what I got.
That's right, you got that. You add all these up and you get that.
And then you divide that by this.
Divide that by 5.
Because it goes,
Yeah,
exactly.
and then take the square root of that.
27.5. You
You
divide
take the square root. You don't multiply, you take the square root. Remember, the square root is the number that when multiplied by itself gives you that root.
So you probably need to go to your scientific calculator. You know, reverse that. Okay, the square root symbol is, where is it on here? Square root. So you want the square root of 27.5.
5, 2, then we take that, or 5.2,
That equals 5.2.
no, divided by the 124.3.
Yeah. 5.2 divided by 124.3. And then multiply it by it, and that's 4.2%.
Okay, cool.
All right?
Yep, I witnessed that.
Yep. Remember, don't forget the square root. Right?
Thank you.
You're welcome.
I was starting out like, what am I doing wrong here? I think that.
Yep. All right. Okay, so let's take another break, and then we'll come back and talk about percentile.
All right. Cool. That makes so much more sense now.
Okay, we'll start off actually looking at what we call z-scores, which are standardized values, which is a measure of how far above or below the mean a specific thing. We use these to determine, banks use z-scores to determine risk for loaning money, giving credit cards or doing mortgages or anything else. They look at a wide range of data that includes your financial situation compared to this financial situation of other people who are able to maintain, who are able to service their debt, on the assumption that their financial position will not degrade precipitously through job loss or that sort of thing. Yeah. You all right with this, Rich?
Mm-hmm.
All right. We're trying to stay within some boundaries here, not get into a lot of statistical theory. So anyway, I'll be back. Yep.
Not really, but I can do it. Yeah, this is nothing. Yeah, that's what I need for you.
Like that. All right. I like it. That's all right. I do know. I can never go over the stories from my story. I don't have constant updates my student pool. So I'm like, everything. That's what I actually have. Just randomly generate, like, actually, can I do that? You know what I'm saying? So just, you know how to connect it to what? Mix adding here. So
All right. So what is the purpose of a standard deviation? The standard deviation is a way of looking at data to tell you if it's within or outside what we define as the normal range of data for that particular data set. Now remember, the reason we calculate standard deviation is because depending on the data set, it's going to vary. We just saw that the standard deviation for the three numbers, 1, 3, and 14, was 7. And the standard deviation for the number of words men speak during a day was 8,500 or 8,600. So it depends on your data set. So the standard deviation is really a measure of distance from the middle of the set, what we would think of as the norm. And for small data sets like the 1, 3, 14, they have a bit less meaning because the standard deviation from the is actually greater than the mean, right? So when you have something like that, then what you have is a data set that kind of analysis really has no benefit. However, we've got 186 men and 215 women in the spoken words database. And these variations are, the variance from the mean, 55.1%. That is a pretty big variance. Okay. And 45% is actually a pretty good sized variance. And that really is something to consider. Remember, we said that one standard deviation in a fairly standard bell type curve, one standard deviation from the norm is about 34% of the data set. 34% on either side of the mean means that 68% of the data set falls within one standard deviation. 95% of the data set falls within two standard deviations. So what we say is that anything outside of two standard deviations is considered outside the norm. Okay, does that make sense? Yeah. Yeah. So 14 is outside the range of our data, right? So, that number has no meaning. And that's one of the problems with small data sets. Small data sets may be compact. The three numbers might have been 1, 2, and 3. Okay, in which case the total is 6 divided by 2 is 3. Right, 6 divided by 3 rather is 2. So we've got -1 squared, 1, 0 squared, 0, and 1 squared. We've got 2 divided by 2. The standard deviation of that set is 1. Okay. Well, I mean, we can look at that and say 1, 2, 3. The mean is going to be 2. That's obvious. And then 1 on either side. But you have no way to get to a second standard deviation in the data set. So small data sets are not amenable to this kind of calculation. That's why, but we use the small one just to show how it's done. Because otherwise, if we've got, your book does have that table, and you can download the table either from the CD in the book or from the text CD that's in Canvas. and you can put that into a spreadsheet and do all this analysis on it very, very easily. You all know how to use Excel. So you know you can set this up and do all of the analysis that you want. You can sort the data. You can calculate mean, and you can sort the data and just go right to the median. You can see if there are modes, which there probably are, but they're going to be small. And you can then calculate standard deviation. There are calculations in Excel that allow you to do that, or you can even do it by hand. But we do this. So what happens is a z-score for any value. When we talk about a z-score from the mean, any one value of the data lies, and it's calculated for a sample, and we have the analogous calculation for a population. But it's calculated for a sample by simply taking the difference between the sample and the mean. So the z is x minus x bar over s. S being the standard deviation. And what this does is give you essentially a number of standard deviations. So anything between 0, which would be a number that was right on the average, on the mean, to 2 plus or minus 2 is within normal range. Obviously, so all we're doing is calculating. So the z-score immediately tells us whether something is within or outside the normal range of expectation. So in the case of, let's just take a look at one bit of data from the study of the number of words men speak. Go to that appendix. We'll take a value, 27,531. We're going to subtract the mean. We have that back in the book. Page. Minus 15,668.5. And we're going to divide that by the standard deviation of 8632.5. So someone want to do that?
Uh, 1.37. So 1.4.
1.37. We'll take it out to 2 decimal places. Okay, so that's our z-score. What that says is that that value is 1.37 standard deviations away from the mean, which means that it's within the normal range. Anything under 2 standard deviations, a score between z-score between -2 and 2 minus 2.0 and 2.0 is considered within the standard range, within the normal range. Anything above 2.0 or below minus 2.0 is considered outside the normal range. It is not considered within the normal range. So if we were looking at say, again, automobile repairs, and we had automobile repairs for similar damage to a car from, say, a dozen different repair shops, which is what people have done. They've done basically the same kind of damage to, you know, cars and the same cars and everything, and taken them to you know, a multiple shops and just, you know, had them, you know, do the repairs. So we're going to get a range of prices. Considering that there's a lot of competition in auto repair, those prices are largely going to fall in a similar range. Will they be exactly the same from one shop to the next? No. But they're going to fall within a range. But then occasionally you have something that's going to be either very much higher or very much lower. So what you want to do is look and see if those are outside the range. So we calculate the z-score. It's just an easy way of determining how many standard deviations away from the norm any particular bit of data may lie. Make sense? Okay. So we will be going back to z-scores later in the class, probably in week 4 when we look at standard curves and how do we basically from a data from a plot of data, how we can read a standard deviation. Fairly straightforward way to do it. Okay, that makes sense. I'd like to move on to a couple of other topics. So we're talking about basically data. So let's take a look at a data set and look at the concept of percentile. You've all seen percentiles. With your kids, you have kids that have growth charts, and those are percentile charts. What a percentile is if you look at one value, you look at the number of values that are less than that value and divide it by the total number of values in the data set. So let's just take a look at, we have 100 values, and we're going to just say we've got 1 through 100. So we have 100 values, and we want to know what percentile is the score 71. Well, 71 has 70 numbers less. 1 through 70 are all less than 71. So 71 is at the 70th percentile. 70 divided by 100. So it's the number of values less divided by the total number of values. 70 divided by 100. So it's the 70th percentile. This is why no one can be above the 99th percentile, because you're at the top of the range. It doesn't matter if you've got 100 values in the entire range, or if you've got 100,000 values. You can get 99.99, etc. percentile, but nobody can get to 100 because there's always your value is taken out of the total. So it's everything below yours. So that's why we see 99th percentile for, you know, like growth charts for our kids. You're at the 99th percentile, meaning that you are that you're the top of the list. You're 99% of the babies are going to be
below you. And that can be in a lot of things. We had this when our child had a head injury at 9 months before her fontanelle closed. We determined this happened because her head started swelling up. And our PA said she's at like the 99th percentile for circumference of her head. There's a problem here. And that's when we found out she had fallen and had a head injury. So a lot of times in medicine, we use it to determine when there's a problem that has to be addressed. If you're sitting at growth charts, here's a good one for you. Years ago, we had nothing. There was little we could do safely for people who were at the very bottom end. I had a student one time who, when she was 5 years old, she was at the 2nd percentile for height for her age group. Very. They fortunately at that time, recombinant human growth hormone had been marketed, and so she was given human growth hormone, and she pulled up to about 30%, which is reasonable. She was still short, but not, she didn't walk in the door with a 28-year-old face and the height of an 8-year-old. Yeah, well, it's also a source of discrimination in our society. So, this is not good. So anyway, but we use these kinds of data in medicine. We also look at performance of businesses. When you have how do people like Kmart decide which stores to close? Well, they look at where they sit in terms of their level within the corporation of sales and profitability, and they will try and fix it. But if it looks like they can't, that's how they make decisions for close. That's one of the criteria they make for decisions to close stores that are underperforming. They look at their percentile rank of all of their stores. Yeah, well, yeah, Walmart is real economy sensitive. A lot of people who, when they have money, would say Walmart, suddenly find themselves walking into Walmart because that's what they can afford. Well, they do. I mean, I've known people that have said, "I'll never shop at Walmart," and you find out that, "Oh, I got that at Walmart." Okay, okay, change your mind. But I mean, it really is, and um, that's just reality. But I'm not surprised. Walmart has closed a few stores, but they're also getting to the mega Walmarts and the mini Walmarts. So they're finding, I think, that those two are the ones that are doing well now, for whatever reason. But anyway, but businesses do that too. So what they look into that sort of thing. So we actually look for so what we do is we define again we define percentile as being in a data set as being the place where that percentage of the data is actually below the position you're looking. So we can go the other way, and we can actually convert a data value from knowing the percentile. If we know the total number of values in the set, and then we know the percentile that's being used, okay, then we can calculate then we can calculate what position the specific data point that has a percentile associated with it comes in. It's just algebra. So what we do is we look at that number. Just say you have somebody says, I'm in the 85th percentile for whatever. And so if you know what the data set is, you know that 85% of that data set is below the person. So then you can calculate what position that person sits simply by knowing the number of data points. You can calculate the percentile divide, percentile is given as like a whole number, 25th percentile. You divide it by 100 and a fraction, and then just multiply it by the total number of data points, and you know what position you are, if that's of interest to you. Okay, so let's look at another variation on percentile, which is the quartile. And the quartile, really, let's talk about how data can be looked at when it's raw data. I'm going to go back to the board. Let's just say we have our data and we can put it on a line. We have a minimum and we have a maximum. We know from the minimum and maximum what the mid-range is. We simply add the minimum and maximum and divide by 2. So we know the mid-range. Okay. So if we look at the data, I'm assuming that the data is rather smoothly distributed across this line. This is a simple idea here. The first quartile, we'll call it Q1, is 1/4 of the way between the minimum and the mid-range. Quarters. Q for quarters. Another word for mid-range would be the second quartile. And then we have the third quartile, Q3. So this is 25% of the data. And this is 50% of the data. And this is 75% of the data. Right? So that's if you have a nice smooth progression of data. We can divide it up into quarters pretty easily. But let's take a look at another set of data that may not be so easily, that may not be nice and smooth. Let's take a look at a data line where we have the same distance, only I'm going to mark data here. So we're going to have data at our minimum, and we're going to have data at our maximum. By definition, we have to have a minimum and maximum, right? So let's just say that our data here is distributed in this section. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I think I'm going to add 14, 15, and maybe 16 for that. Make it easy on myself. Okay, so here we have the minimum. Here we have the maximum.
And the data range can be described in that way by putting basically a boundary along our data line. But where is Q1? Remember, 25% of the data are below it. So we're going to have 4 data points below. First data point, second, third, fourth. So this is our first quartile. 1, 2, 3, 4. This is our, remember this, our mid-range is actually in between these two. So this is Q2 because 50% of the data is below. 1, 2, 3, 1, 2, 3, 4. This is our Q3 because we have 75% of the data below that. So we have our data now is very much skewed. So this is the basis for what we call a box plot. In a box plot, we do lay out a line that tells us the extent of our data, and then we create between Q1 and Q3 a box that defines the middle 2 quartiles. They don't, the sections of these boxes don't have to be the same size. More or less here they are, but they don't have to be the same size. Again, we are at 50% of our data is in the middle of this box. Okay. So if you remember from the normal distribution of data around the mean, this is roughly a standard deviation. I say roughly because it's 50% as opposed to 68%, but roughly. So there's a variance there. So the rest of these data points are shown going out, and then we put basically a line that goes through all of the boxes and stuff, and we just have it lined out. So a box plot is a way of very quickly, again, seeing how the data is skewed in one direction or the other. It's a way to really see where the outliers are. Because of course, here, if we looked at this plot where I said everything was sort of even, you've got your box pretty much set right bang in the middle of the plot. And either side, if the data are truly evenly spread out, either side of the middle of the mid range of the data would be recorder. Either side of Q2, which would be the median of the data, right? Same size. But box plots don't have to. Nor do the use of the variation there require. Nor does the distribution have to be perfect. Okay, so there are some other terms we use. The interquartile range is just the difference between Q3 and Q1. Okay, that's where we have most of our data. The 90 percentile range, we can calculate the percentile position of any data point. Here we have, I put in 16 data points. So 15th data point is going to be about the 94th percentile. Or rather it's going to be about the 88th percentile, because 14 out of 16 are less than it. So we can actually calculate percentile ranges as well. The
Any data set can be given what we call a 5-number summary. The minimum, Q1, median or Q2, Q3, and max. 5 numbers describe all of that. When we know what those summaries are, and we're talking about the value at those levels. So the value at Q1 that sits at Q1 in our box plot is what we're talking about. So in this case, the value at Q1, whatever it is, let's just say our numbers go from 1 to 16, just to make it easy. Our value of Q1 happens to be 4. Our value at the median is 8.5. Okay. Our value at Q3 is 12. And then our maximum is 16. So we actually take the values. Those define it. If you know what those are, then you can actually visualize what the box plot's going to look like. Okay. And you have to, and so that's if we had a smooth curve that would look like. But notice that the values are still the same. Whether if we've got 16 evenly spaced values or 16 values skewed toward the low end, the structure is still the same. Our data points are there. So we use the same values. So when we are talking about the 5-number summary, this is also known as a box and whisker diagram. Whisker because you have all these lines and stuff on it that are sticking off. And we draw our lines at the first and so forth quartile. So a lot of times the box plot will not have anything except the box and the minimum and the boxes, the minimum and maximum, because the boxes define Q1 and Q3 and the median. So we have lots of examples. I'm going to give you the example. If you look at slide number 77 in the PowerPoint, you'll see a box plot of movie budget amounts. And this is actually from a fairly large database. Okay. So the minimum is 4.5 million. I presume these are millions. The maximum is $225 million. That seems like a lot, but it seems to be getting more and more common in movies these days. But if we look at it, the median value is $68 million. That's still a pretty fair piece of change. It's not an independent, it's not an indie. But it's, you don't?
What?
All righty. You're kidding me. That's really annoying. You're right. Well, guess what? You now do. Sorry about that. Okay. All right. So slide number 77. I'm sorry. I do apologize. I just forgot to make that one visible. I'll make sure that next week's are obviously visible. So if we look at that, our box plot is very much skewed because it's based on the median. The median in a range of 4.5 to 225, 225 is a lot of money to spend on a movie. So most movies are going to fall in a much lower range, well under 100. So we have our median at 68, our first quartile at 35, our third quartile at 113. So our 5-number summary is 4.5, 35, 68, 113, and 225. that lays out what the box plot looks like. Now, if we don't have the exact data, we can, if we try to proportionally move our, stretch out our line, we can approximate what this looks like. But it gives us a good idea. We know that 225 is way outside the third quartile. Okay. That makes sense? Okay. Now for a normal distribution, in this case, number 78, we're looking at random sample of women. So here we have a sample of women. Our population is women. And our sample is, we don't know how many. So it's probably height in inches, 59.1 inches. So that's just under 5 feet, to 67.8 inches, which is nearly, which is 5 foot 8 or so. So that is the minimum. The first quartile is 61.5 inches, just over 5 feet. Second, the mid-range, the second quartile, the median, is 63.3. The third quartile goes to 64.95. This probably is in between two measurements to get to that second decimal point. And then our max is 67.8 inches. That's of this data set. Does that generate out to all women? No, I know women who are 4 feet tall. I also know women who are 6.5, 7, close to 7 feet tall. So it's not obviously all women. This is a sample. But what it does is it tells us it in a large enough sample, it's going to be pretty much a normal distribution, because height is a continuous data, is a continuous type of quantitative data. Okay. Skewed, well, okay. Again, we're looking at our salaries of NCAA football coaches in number 79. Clearly, the middle of that, the second quartile, in other words, the median, is $205,000. Okay. No, our first quartile is 205. Our median is 300,000. Our third quartile, 638.44. You going to live, Nate? Good. And then we have our outlier, 2.84 million. Okay. So we have that's what a box plot can look like. It's a good way of looking at skewed distributions. Yeah, it's a good way to look at skewed distributions. An outlier, we have outliers. We know that outliers can have an effect on the mean. They can also have an effect on the standard deviation, because they are part of the data set. Okay? Because we calculate a mean. It can also change the scale of a histogram, because we have to have all this stuff way out there. And we're going to end up with, as a histogram, we're going to end up with a bar that's very high if we're looking at salaries as being the number. Okay. So it can really skew that. We can look. We can modify our box plots so that we define an outlier that is above Q3 by an amount greater than 1.5 times the interquartile range, which, remember, is the range from Q1 to Q3. So an outlier, then, if we go back to this thing with the football coaches, the interquartile range is 205 to 638. So the interquartile range is 433.44. Well, the difference here 433, the interquartile range, we look at the difference here between 6840, it's nearly $2.2 million. Clearly, that's more than 1.5 times the 633 or the 433 interquartile range. So that's another measure of something that's an outlier that is useful in these very skewed data sets, and more so than trying to calculate a standard deviation. That one would definitely be beyond 2 standard deviations from a mean. But it doesn't give us a true picture as to how far outside what is normal. What we consider with a box plot is that the interquartile Q1 to Q3 range is largely normal. We can also have things that are way below. We can have data sets that have that are skewed by having numbers that are very, very low. I think if we looked at a box plot of the data for men talking, remember there was one that was like 1,118 words in a day. My bet is that he would be considered an outlier because he'd be way down, okay, in the data set from the bulk of the rest of the data. There are a few others as well, but rule of thumb, okay, again, we look at outliers and we try to determine whether the outliers need to be included in our analysis or if there's a rationale for making them a special case. And we do that. We treat, in something called a modified box plot, we treat them as special cases, special points of data. When they're way outside the range, we have to ask ourselves why. In the case of NCAA football coaches, obviously, well, it's that, and some schools, football is a more important program. It's a money-making program. You go to Penn State, they have quite a program. Nebraska, Colorado certainly overpays its coach. I mean, by standards of like University of New Mexico or someplace like that. So we look at the last value in our modified box plots. We look at the last value, whether it's the lowest value or highest value, that is not an outlier by the calculation of 1.5 times the interquartile range. So we can modify our data in that way. Now we can modify the pulse rate data. Let's go back, and if we look at slide 86, we're looking now at a box plot of the female pulse rate data. Remember, there were 2 of them that were way out at 104 and 124. But if we look at the minimum, which was 60, the median was about 74, and we have our quartiles starting at about 68 to about 80. And then the rest of our data out to 96 or something like that. If we look at the interquartile range at 1.5, that line to the left or to the right of Q3 is about 1.5 times the interquartile range. And so what we're looking at is those 2 dots are taken off the line of data, but they're still there so that we know they're there. We don't hide the data. We don't eliminate the data, but we show that it can really modify the data. Okay. So we treat them as special points. I don't know if, all right. So I think that's pretty much what I wanted to do. What I want you to do now is make sure that, I'm going to make sure that, yeah, chapter 4 slides are available. The chapter 4 notes are the definitions for that. So let's take a quick look here. And we'll do a share. And we'll do a desktop. All right. So let's take a look at what we have in week 3. It's chapter 4. Chapter 4 is probability. I need you to read that, and we will go over. There will be a couple of other things that we'll go over next week, but we'll have. What I want you to do is go through that chapter. We'll do a quick review of basic principles of probability, and then we will spend the rest of the class on Wednesday working on the homework for next week and perhaps answering questions for the homework for this week. Okay, we'll do both. Because we lose a class, I need you guys to do that work, and then I'll be prepared for us to really work together on problem solving next week, and a lot of examples. Okay? All right? Gotcha. Gotcha. Pardon? Mm-hmm. Discuss the value of an equation. Well, one of the equations we just threw up on the board was the equation of the standard deviation, right? We've also got equations for calculating means. That's exactly right. If they're outside of the normal range that they expect people to be able to service a loan, then they would probably outside below. Outside above, they don't care, right? You got enough money, you can get a loan for anything, right? But they do look at that, and they look at the data, and they've got millions of data points for doing that. But z-scores can the calculation for a z-score or the coefficient of variance discuss what value they have. And I don't, I'm not going to put any restrictions. If there's some, we've talked about some other formulas here. You're welcome to do that. And go through the chapter and take a look at stuff we may not have covered. You can look at percentiles. There's a formula for percentile. Okay, so formulas that we have used, statistical formulas that we've used in this class. Does that make sense? All right. Yeah, I'm not expecting you to go rooting through the book and finding something we haven't covered. Because we're not going to cover everything in this book. It's not possible. This is a full semester course at most schools.
Is there 2 statistics classes? This is like 322s or 422s?
There is in the bachelor's programs, there's just statistics, and that's this one, and algebra.
Oh, cool.
Did you do the algebra online?
I did the second time.
Good.
I did. Yeah,
Okay,
I passed
good.
it today.
Good for you. Glad to hear it. So yeah, that's the only math classes you take. I mean, obviously you've got accounting, which is sort of math. It's definitely applied math. Yeah, it's addition and subtraction. The trick is figuring out which one you do, and where things go, and then calculating those ratios for analysis. That sort of thing. But yeah, but this is the only statistics class you're required to take.
For some reason, I like statistics. And I don't know if it's just like I like algebra to like the beginning part, but then like you start getting into all the like trinomials and stuff like that, and I'm just like, I'm not going to use this, and that's when I was having a hard time staying focused.
Yeah, my explanation for why we do that, it's really to teach you, is to give you practice with thinking about problems and how to solve them. Because yeah, you'll never use a quadratic equation in your life if you're not an engineer or a scientist.
Right.
You just won't. I'll be honest with you. You probably won't ever calculate a standard deviation in your career. But understanding what they mean helps you understand what my greatest emphasis is in this course, which is how are statistics useful and how are they misused?
Yeah, and that's already, I've already learned a lot. What is this really saying?
Yeah.
This is what they're saying it says, and they have numbers, but if you really look at it, how much
What is it?
information is true?
How much is, yeah. And, they can throw numbers out until you're drowning in them.
But it doesn't
And
mean
that's what a lot of them do. I mean, I see this especially in propaganda. When people start throwing numbers out, it sounds real until you actually get into it and say, they didn't say anything.
oh, this scares you into
It's
believing
just razzle dazzle. Baffle them with your BS.
Hey, that's my degree. What can I say? Hey, you guys have a
Well,
good
we
day.
hope that's not going to be too baffling. Yeah, have a good weekend, and we'll see you next Wednesday.
Yes, sir.
So, how are you doing, April? You going to be able to be okay? I need you to really buckle down and get to homework. And remember that if you run into a problem, you can always email me. I do check my email even when I'm not working. I'll check it at least once or twice a day and try to get back. Brandy will tell you that. Gotten back to her several times on a weekend when she's asked questions. So I'm perfectly happy to do that. And remember, Wednesday is gonna be a day for, really trying to catch up on everything and apply probabilities. No, it's not due until the end of next week. It may show this week, but I will not penalize you if it's at the end of next week that it comes in, because we really aren't going to do anything with it until the last week of class anyway, when we talk about the LRA and what it means. Okay? Make sense?
Yes.
Have a good weekend, everyone.